All right, so welcome to Theory Seminar. It's my pleasure to introduce Dimitris Achlioptas, who known for a long time because he was a researcher at Microsoft Research in Redmond while I was a PhD student at the University of Washington. And then, like many great people at Microsoft Research, he moved back to the university system. And he's a professor currently at UC Santa Cruz and also at the University of Athens. And you know, when I invited him here, I thought, oh, it's no big deal. Fly from the Bay Area to Chicago is really easy. But it turns out this fall he's in Athens, and so that's much harder. But he came anyway, which is fantastic. So his main research area is in random processes and structures. And so he studies algorithms on random structures like random graphs, and he studies the properties of random structures like random graphs and random Theorems and the barriers for hardness. And so he's going to talk about some of these things, I think.
Thank you. Yes,
Oh, and I wanted to mention that there's a student meeting with him immediately afterwards from Club the One if anyone wants to stay and chat.
it's true that I know Jason for a long time, and he didn't always used to dress like this. He used to dress very differently.
Wait,
Okay.
He's come down since he moved here, actually.
Pardon?
He's come down since he moved here.
I see. Today, I mean, this was quite something to see. Anyhow, so the title of my talk is Algorithmic Barriers from Phase Transitions. And to keep the context sort of concrete, throughout the talk, this is going to be the setting. But at about 3/4 into the talk, I will actually show that the main ideas transfer to other areas. So throughout the talk, the setting is going to be that we have some collection of variables, and there's always going to be n variables. And all these variables, you should think of them as having the same small discrete domain. So this could be all binary variables. And there's going to be also a collection of constraints. And the number of constraints is always going to be m. And the point is that these constraints are what a physicist would say frustrated. Meaning, each constraint is happy if the collection of variables on which it depends takes a subset of their possible values. And different constraints sort of want different things. So the question is it possible to satisfy all the constraints simultaneously? So graph coloring is a problem I guess most of you are familiar. We're given a generic graph G, and the question is it possible to assign colors to its vertices so that adjacent vertices that are connected by an edge, have distinct colors at their endpoints? So one way to model that problem in the formulation I showed is we think of the vertices of the graph as the variables. Each of the variables has domain, the integers from 1 up to k. And then each edge in the graph is now a constraint that binds two vertices, two variables, and says, look, among the k² possible values that you can take jointly, so k colors for you and k colors for you, so k² combinations, I am unhappy with k of these combinations, the ones in which you both take the same color. Okay? So each edge of the graph can be thought of as a not equal constraint on two variables. Another very classical problem is satisfiability. Now this time, the variables are binary rather than being k-ary, and the constraints are k-ary rather than being binary before. So we have sort of the two extremes between graph coloring and satisfiability. And when I say that they are k-ary, what I mean is that each clause, this is a clause, is the logical OR of k variables or their negations. We call these literals. And for example, this says, out of the 8 possible value assignments to these 3 variables, I'm happy with all of them, except for 1, 0, 1. Okay? And then I use white and red to indicate whether a particular clause wants a particular variable to be positive or negative, 0 or 1. So this is denote negations. And in this particular framework, one can model a bunch of different NP-complete problems. And what I will be looking at is random instances of such constraint satisfaction problems. So first, let me explain what I mean by random. So just like before, each constraint is going to be binding a very small subset of the variables. So if it's an edge in a graph, it binds 2 variables. If it's a clause in k set, it binds k variables. K is fixed, while the number of variables, we will think of it as growing. Okay? The sense in which the instances are going to be random is that the choice of variables bound by each of the constraints is going to be uniformly random. So if you want to add an edge, you select 2 vertices / variables at random, and that's where you put it in. If you want to add a clause, you select k variables at random, and that's the clause that you add. And out of the 2 to the k possible orientations, you select one of the 2 to the k uniformly at random. Okay? Another way of thinking about it is you take the generic constraint satisfaction problem that you can have on n variables. You put all possible constraints that you could have on these n variables in a bag, and then you just start drawing from that bag uniformly. Okay? One thing which will be true throughout the talk is that the instances we will be looking at are sparse. And by sparse, I mean that the number of constraints is going to be linear in the number of variables. This is the most interesting regime, it turns out. And this parameter, which is the ratio of constraints to variables, this ratio, I'm going to sometimes refer to as the density of the problem. Okay? Now, let's look at some of the things that sort of are immediately true about these instances of constraint satisfaction problems. This graph, by virtue of the randomness in these edges, is an expander. It's actually a fantastically good expander. Which means that if you look at a random instance, you are not going to be able to find a small number of edges in this graph such that you can split the graph into 2 parts of roughly equal size while cutting few edges. Okay, so these graphs do not have small separators. Another way of sort of saying essentially the same thing is that if you look at the shortest path metric induced on these graphs, so for every pair of variables, let's say, you say, what's the length of the shortest path between us through different constraints? This induces a metric, the shortest path metric. If you wanted to represent this metric in a geometric way, meaning you would like to take the vertices of the graph and put them in some geometry, so that distance in that geometry was a good approximation of the graphical shortest path distance, you would need a very high dimension to do it. Essentially, you would need as many dimensions as the number of variables that you have. Okay, so they're not compressible. There is no low geometry in which you can put them in. So already, the absence of small separators is a little bit scary from an algorithmic point of view. So you're not going to be able to do things like embeddings or dynamic programming on tree width or anything like that. And then it gets a little bit, it gets a bit worse in the following sense. If you've taken sort of a basic course in random graph theory, one of the things you learn is that if you look into such a graph, if you take a vertex and you do breadth first search from that vertex, then for any finite depth, the graph that you're going to see is going to be a tree. Okay, this is by analogy to sort of a branching process. And it kind of makes sense. I mean, you know, you have this vertex V1, out of a linear number of constraints, you pick a finite number. So they're going to be distinct. And then each of these picks a finite number of variables on the other side. Those are also going to be distinct. So you basically get a tree for quite a while. Okay? Now, if we look at the graph coloring problem, we will shortly see that if, let's say, the density of the graph is 10 or something, you need at least 4 or 5 colors to do it. So if the average degree is 10, you need something like 4 or 5 colors to color the graph. Yet, if you look at from the point of view of any particular vertex, so this is the vertex, these are its neighbors in a random graph. These are its neighbors, these are its neighbors, these are its neighbors. This is a tree. A tree is always 2 colorable. Okay? So locally, the graph, from the point of view of every vertex, looks bipartite. But the truth of the matter is, the graph is not bipartite, and you're going to need a lot of colors to be able to color it, which means that the reason that you need a lot of colors is a global reason. Okay? Locally, you don't get any information about how to correctly color the graph. Okay, so this is another source of hardness in these problems. So this is what I mean by say that the graph is locally tree-like, and it also turns out that it's a tree and it's almost like a regular tree. So just to drive that point home, if we wanted to do random graph coloring, just like before, each vertex in the graph is a variable with domain 1 to k, and each edge simply picks two variables at random, right? So to stick an edge into my graph, I just pick two vertices at random. So this is what I do. So in the sort of language of random graphs, this is a GNM model. I have n vertices and m edges. The two vertices are chosen randomly. And it turns out if you really wanted this to be a random regular graph, so that every vertex has the same degree, for example, you could do that. It's basically, so here you have a balls and bins experiment. Each of these things throws two balls on the other side. Okay? So you could model this as a balls and bins experiment in which you condition that all the bins receive the same number of balls. And this gives you a uniform random regular graph. So you can deal with regularity, you can deal with general degree sequences, you can deal with a lot of different problems. So satisfiability is sort of similar. If you want to do random k-sat, you say, look, there's n choose k possible ways to pick the variables in a clause. After you've picked the variables, there's 2 to the k possible orientations. Put all these constraints in a bag and start drawing independently from that bag. Is there a question?
Yeah. So this global versus local property, if we were to relax, like absolutely solving every constraint and
No,
just like
it doesn't go
does
away.
that mean that
It doesn't go away. If you want to do max sat, you can get something just by locality, but you cannot get what you should be getting just by locality, because you still have global correlation at the max sat level.
Say two colors, I don't get almost the whole thing?
Two colors is a special case, right? Because that's bipartiteness.
No, I'm saying is you take this graph that you
Yes.
had, which you said was probably 4 or 5 colorable,
That's right.
given the global constraints, but the local constraints look like they're too colorful,
Correct.
right? If I just say, well, color as best you can with 2 colors,
Yes.
right?
No, what happens
Can I
is
do okay, or?
no, you will lose a linear fraction of edges. Because what happens is it looks like a tree, and then you reach a critical depth, and then boom, a ton of cycles emerge simultaneously. The emergence of cycles is sort of related to the birthday paradox. When this boundary acquires size about square root of n, now every time you add something. So square root of n does take logarithmic depth to happen. But when this becomes about size square root of n, then every constraint that you add causes a lot of trouble. So the main point I wanted to drive so far is that we have this generic presentation, variables on one hand, constraints on the other. Each constraint buys a random subset of variables. The constraints can be of many, many different types. The important part is that they're selected uniformly and independently, and that if you look at this graph does not have any low-dimensional representation. Are there any questions up to this point? Okay. So now you might say, I mean, you know, why bother with random problems? And this is sort of the one philosophical slide in the whole talk. Now, we certainly don't care about random problems because they look like real-life problems. So if someone says this, they're lying through their teeth. Okay. The way my reason is as follows. Imagine, let's say that I'm doing, let's say, random satisfiability. Okay. So I have n variables, and then there is this bag of all possible constraints, of all possible clauses of length k. So if I don't draw anything from the bag, then everything is a solution. So all of 0, 1 to the n, the entire hypercube, is a solution, yes? Then I put my hand in the bag, I draw one constraint, and observe that a single clause kills this many assignments, because it says, look, these k variables cannot take this combination, but all the other n minus k, they can do whatever the hell they want. Okay? So if k equals 3, with a single clause, I killed an eighth of the entire cube. Okay? Then I draw another clause, and I kill another eighth of the cube, except for the fact that they intersect. Okay? So what's happening is that I have this piece of marble, basically, and I am taking away huge chunks away at the time. Okay? So my capacity to shape this object is limited by the fact that I'm using only very, very coarse chisel. I can only take away huge parts at the time. Another question is it possible with this very crude tool to create a set which is difficult to distinguish from the empty set? Okay, because that's what satisfiability is about. Does that make sense? Clearly, if I was allowed to kill one truth assignment at a time, it would be trivial to create a needle in a haystack. But to kill one truth assignment at a time, I would need to have an exponential description, okay, of my object. So P versus NP is it possible to have small objects act on big spaces and create complexity that is difficult to distinguish between being able to act on the big space directly? So if my goal is to create difficult satisfiability instances, this is equivalent to say, I would like to create satisfiability instances whose sets of solutions is hard to distinguish from the empty set. Okay? And a reasonable way to try to do this is to take the original cube and try to basically, remove solution in as uniform way as possible. Okay, to thin it down to a set that is marginally close to empty, but it's not. And a great way to do that is by doing it at random. Okay. So I randomly bombard the cube with constraints until I reach the point where I'm very, very close to have killed everything, but not quite. And what my hope is that what I have is left as a picture is very close to what would have happened if I was killing one constraint at a time. Okay, that's the motivation. Moreover, as it turns out, although the instances themselves, random instances themselves, are very different from real-life instances, algorithms that work well on random instances work extremely well on real-life instances. So random instances have driven a lot of the developments in algorithmic progress in constraint satisfaction problems.
See, that seems very counterintuitive to me, because I would have thought that algorithms work better by exploiting known structure of the problem.
Yes. So that is the easy part. By which I mean the first thing that you should try to do is if you can decompose your problem, great. So a lot of the real-life structures are encodings of engineering artifacts. We humans are not very smart, so our engineering artifacts tend to be localized. So there's one component that has a small interface to another component. Yes? So this part you should do. But following that, how do you analyze a single component when actually there is some human intelligence reflected in here? It turns out that using algorithms that do work on random structures gives you very good performance inside each component. So for example, stochastic local search works extremely well. And it turns out that tuning your stochastic local search algorithm on random instances gives you results that work very well in practice. So this is sort of the high-level motivation. And now I will say that in a certain sense, when we start talking about random instances of constraint satisfaction problems, we have a tremendous amount of control. So here's a theorem about the chromatic number of a random graph. It says for every real number r, that's the density, the ratio of edges to variables. So this is basically half the average degree. With probability that tends to 1 as the number of vertices tends to infinity, the chromatic number of a random graph with n vertices and r times n edges is either k or k plus 1, where k is the smallest integer such that r is less than k log k. So, for example, if you tell me that your graph has 6.73 times n edges, so the average degree is a little bit above 13, then I can prove that with probability that tends to 1, as the number of vertices goes to infinity, the chromatic number is 5 or 6. Okay? If, on the other hand, you tell me that the average degree is 10 to the 60, then I can tell you with high probability the chromatic number is this or this. Okay? So this is an extraordinary amount of accuracy. Okay, we know exactly how many colors you need. And in fact, if you look at the real line, we can partition it into intervals. And for about half of them, we can tell you one number, not even two numbers. If this is the density, this is how many colors you need, period. Nothing to discuss. Okay? So, on the other hand, if you look at the arguments that establish this knowledge, they're not constructive. They don't give you any information on how to find such colorings. They simply say they exist. Okay? So, if we go into the algorithmic realm, the things are actually really, really sad. So consider the following algorithm, okay, for coloring any graph, but we will think of it in the context of coloring a random graph. It basically, ignore the first line. The algorithm is ignore reality forever. Don't even bother looking at the graph. Unless you get into a situation that you should completely panic. Okay? So there exists a vertex such that its neighbors have already received k-1 distinct colors. So now the color for that vertex is forced. Okay? So with the exception of giving priority to the most obvious of situations in terms of what to do, okay, just continue to ignore reality as much as you can. So this is very similar to how the Greek economy is run. So that's how what you do, okay? So is this algorithm clear? Okay.
Who supplies the constraints?
Who supplies the Germans? I mean, come on. So, okay. So this is the algorithm, and if you apply this algorithm on a random graph, it actually doesn't do very bad. Remember that if you have k available colors, you should be able to find the coloring as long as the density of the graph is k log k. Okay, less than k log k. So this algorithm will get you half the way there. Okay? So you can flip the statement around and say that this algorithm uses twice as many colors as necessary. But because of this talk, it'll be easier to phrase it like that. Okay? So this algorithm gets you to 1/2 k log k. And what is really remarkable is that we don't know anything better. Okay? And this is not for the lack of effort. So pretty much everyone who works in probabilistic combinatorics has tried to come up with a polynomial time algorithm which beats this algorithm. Okay? So just to make sure the order of quantifiers is concrete, come up with a polynomial time algorithm which for some fixed epsilon, arbitrarily small, for arbitrarily large k, works when the density is this. Okay? Nobody knows how to do this, and in some sense, the main message of this talk is that we shouldn't expect that to be possible. Okay? So it seems like there is a step function here. We have the trivial algorithm, and when that trivial algorithm stops working, nothing works. Okay?
I have a question about the algorithm.
Yes.
So I can imagine this algorithm always succeeding correctly coloring the graph if it wasn't given the constraint on colors first, but it tries to. So this either succeeds or fails the way you specified it, right? There's some
Right. The
number
way
of
that this
colors
algorithm fails is at some point. I mean, the way this algorithm operates, right, is you color a vertex. So think of each vertex in the graph starts with a palette of k available colors, right? So in every step, you pick some vertex, you give it a color, and you remove that color from the palettes of its neighbors, right? So at any given moment, each vertex has a list of available colors. And the only thing that is intelligent ever is if some vertex has its palette shrink down to 1, then that vertex gets priority. But you could imagine that you have two vertices, both of which have palette 1 and the same color. So when you give it to this one, the palette of that one shrinks down to 0, and that's failure. Okay? We can in fact prove that even if you endowed this algorithm with backtracking, okay, so when that happened, you could go back and remove the color from a bunch of vertices. We can prove that it would take exponential time. Okay? So, and this is a rigorous mathematical statement. Okay? So basically, Either it works in linear time, as it does for densities like this, or it decomposes to trivial enumeration. Okay? So because backtracking taking exponential time is essentially just try everything. Okay? I mean, it's a little bit better than try everything, but it's just a matter of what's the constant in front of the exponent. Okay? Now, for satisfiability, things are sort of similar. Let me explain top and the bottom. There's a conjecture that says that for every fixed k greater or equal to 3, there exists a critical ratio of clauses to variables such that the probability that a random instance of ksat with n variables and r times n clauses is satisfiable, well, the limit of that probability, as n goes to infinity, is 1 if the formula is not too dense, and it is 0 if it is too dense. So this plot corresponds to k equals 3, and the different plots correspond to, the horizontal axis is the density, the vertical axis is the probability of satisfiability, and the different plots correspond to an increasing number of variables. And there seems to be a crossover point where all these guys meet, and conjectures that in the limit you actually have a true step function. Okay? So the existence of this, even the existence of this constant is not known at this point. But on the other hand, we have bounds for it. So in particular, in one line, literally, you can prove that this constant is less than 2 to the k log 2. Okay, this you can do in one line. And then, in half a page, you can prove that it is at least c times 2 to the k over k, where c is something like 1/8. And if you want to increase 1/8 to 2/3, you go to 2 pages. And if you want to increase 2/3 to something like 1.7, you go to 40 pages. And there doesn't seem to be a natural barrier to how big you can make this constant. Okay? Other than how many pages you're willing to write. And indeed, there was a very nice result a few years ago where Amin Khoja showed that you can replace this with log k. Okay? And you can think of this log k as some kind of a universal constant. Okay? So remember this quantity. Similarly, so we have 2 to the k log 2 on one hand, and 2 to the k divided by k times log k in the other. Whereas for coloring, we had something and half of that something. Okay? So, similarly to coloring, we can prove that solution exists for densities that are almost as good as the other. Okay? But again, this is not constructive. We can prove their existence. So for example, if you look at k equals 10, you can reach the following conclusion. If you look at a random 10 sat formula, if its density is greater than 709, there are not going to be any solutions. If its density is less than 704, there are going to be, in fact, a ton of solutions. But every known polynomial time algorithm breaks down when the density is about this. Okay? That's a big gap. So this is a general phenomenon, and you can think of it sort of in this picture. So this is the density of a problem, and for any such random constraint satisfaction problem, an easy argument typically gives you a point such that for densities above this, no solutions exist. The system is over-constrained. Okay? The way that you do that, and there is some reason in which I will explain this, is you say, let capital X be the random variable equal to the number of solutions of a random instance. Okay? Now you can write X as a sum of indicator random variables, one for each candidate solution. And then by linearity of expectation, this is very easy. You get, okay, for any particular value assignment, what's the probability that it is a solution? That's a very easy computation. A result of which is that you get that the number of solutions is some function of density to the nth power. Okay, the expected number of solutions is some continuous function of density to the nth power. So then what you do is you say, okay, what's the density for which this function crosses 1? Okay? As soon as it crosses 1, then when you raise it to the nth power, it says that the expected number of solutions is exponentially small. So it is 1 minus epsilon to the n. Okay? And now by Markov's inequality, if the expected number of solutions is exponentially small, then definitely so is the probability. Okay? That's how you get an upper bound in one line. On the other hand, to the right of this line, the fact that the expected number of solutions is exponentially large doesn't mean anything. Because it could very well be that you have some kind of a lottery phenomenon happening. Okay? The probability that something is satisfiable is very small, but if it's satisfiable, it could be that it has a ton of solutions. Therefore, the expected number of solutions could be very big, whereas in reality, so just like in a lottery, I mean, the expected winnings in a lottery are not that bad, but the chance that you will actually win is incredibly small. Okay? So this kind of argument, just computing the expectation of x, is good enough to prove that you do not have any solutions with high probability above a certain point, but that's all you get out of it. And now, you know, for each of these problems, if you analyze some kind of a naive algorithm like the one I showed you, it will give you a lower bound, so it will say, well, I can find solutions here. But that lower bound will be pretty far from the upper bound. And then if you try a little bit harder, you can improve it, but there seems to be some kind of a concentration point. Okay, you hit diminishing returns. Okay, and this is a very generic phenomenon. Whereas on the other hand, if you are willing to say, well, you know what, I don't care about constructive proofs of the existence of solution, non-constructive proofs are fine, we can get bounds that essentially match the non-existence. Okay, so we have a good delineation of what's satisfiable and what's not satisfiable. And the way we do that is by proving that this random variable I mentioned earlier typically is close to its expectation. In other words, by excluding the possibility of a lottery phenomenon. Okay? So not only is the expectation of x, let's say, exponential here, but the actual variable is going to be exponentially big. So the main question then in this talk is, why is there this big gap? How can we explain the fact that algorithms stop so much further from where solutions exist? Okay. Now, it turns out there is this parallel universe occupied by statistical physicists. Okay? And these people, not only are they ridiculously smart, but because traditionally the job of physics is to interpret nature, their attitude is by any means necessary. Okay, they're not like mathematicians. You know, mathematicians, to publish something, it has to be correct. Okay. Physicists don't have any qualms of that nature. Okay. So they publish something, and then we say, no, this was wrong. Then they publish a correction, okay, and then another correction. So liberated from the burden of mathematical proof allows them to do incredibly exotic things, okay, things that a mathematician will always self-censor from doing. So if they want two limits to commute, they will just do it. You know, it's like a Nike commercial. Just do it. Do whatever it is you have to do. And by the way, they are fully cognizant of what they're doing. Okay, so this is not to say that they don't know that this is illegal a priori. They know it very, very well. I mean, in fact, their mathematical capacity is stupendous. Okay. Anyhow, so these guys have been looking at random constraint satisfaction problems, although they didn't call them that, for a very long time. And by using techniques that are not mathematically rigorous, but incredibly mathematically sophisticated, they put forward a picture about what happens when you add constraints to such a system. Okay? So let me just define one more thing. If you give me a discrete set, for simplicity, we will always, let's just talk about the hypercube, 0, 1 to the n, okay? Now, take any subset of the hypercube that you like. I will say that this subset is convex if for any 2 points of the subset, I can walk inside the set from one point to the other in a straight line, where a straight line means I never have to touch a bit twice. Okay, this is the complete analog of standard continuous convexity. I mean, if you think of a polygon, what does it mean that it's convex? That you take any 2 points and you go in a straight line. Okay, the shortest path is inside the set. So let me say that the same thing is true for a discrete set. For a discrete set, I will say it is convex if for any 2 points there exists a shortest path between them that lies completely within the set. Is that clear? So you can think of convexity as some form of sphericity. Okay, the set is sort of fat. It doesn't have constrictions. Okay. So what the physicist said is, okay, when the density is 0, your original set, let's say the cube, is a nice convex fat set. And then, as you start adding constraints, it will shrink, but it will remain convex. Except at some point, it will shatter. Okay, so it will keep shrinking, but then it will shatter into an exponential number of pieces, each of which is convex. Okay. And then, as you add constraints, you are eliminating these convex pieces. And at some point, there's nothing left. Okay? That's the picture put forward by physicists. As far as the evolution of the geometry of the set of solutions in random constraint satisfaction problems. Is this clear? Is this picture clear? The picture, in certain sense, becomes clearer if you add the third dimension, such that as you move away from the board, you count the number of violated constraints. Okay? So pretend for a moment that you could take 0, 1 to the n and flatten it as a 2-dimensional space. And now above each point, draw a line that tells you, at this truth assignment, how many constraints am I violating? Okay, that's what a physicist will call the energy of that configuration. Okay? So this gives you an energy landscape. And what I have drawn for you is the slice of this energy landscape at level 0. Okay? So the physics picture is that for a while you start off, okay, with a huge basin. Everything is at level 0. Okay? As you start adding constraints and this geometry starts forming, this basin of abstraction starts shrinking, but it still remains one nice convex set, which, as you could imagine, is a fantastic attractor for algorithms. Okay? There is a very nice gradient away from it. And then, boom, suddenly, this set that used to be a single slice now gets partitioned into these exponentially many pieces. So each of these pieces is now the bottom of the valley. Okay? But now there's one valley, and then there's another valley, and then there's another valley moving away from it. Okay? Yes?
So do you think this is surprising? Or did they think this was surprising?
I'm not sure what you mean by surprising.
I mean, I've just been thinking about sort of the size of the constraints versus the size of the set, for example.
The size of the constraints remains fixed.
Right.
You're simply adding more constraints.
Right, but they're pretty small, right? They're not like
Yes.
long-distance constraints.
That's
They're
right.
pretty- So I guess what I'm thinking is that, everything will be fine until it's not fine, having something to do with the size of the set. I mean, I hope that, maybe I'm not making any sense here. I'm not
But remember
surprised
that-
we break into things that are relatively small because the constraints are relatively small compared to the size.
Yes, but this was true also on that regime. The constraints were true also here. Were small also here as well. So I think a better let me try to give it.
I mean, maybe what I'm saying doesn't make any sense. I'm just saying.
No.
I'm not sure I'm surprised by this. Is what I'm saying. Maybe I should be.
Well, in some sense, whether it's surprising or not is not that important. But let me.
Well, it's important to me because I'm trying to figure out whether my model is what you're trying to say.
Well, let me give you an alternative model, and you tell me if that conforms to what you had in mind. Okay. The way I set up the game, there is a fixed graph or if you prefer, there is a fixed collection of vertices, yes? Each of them is allowed, let's say, 10 colors, the same 10 colors, yes? And then I add constraints one after the other, yes? That's how I've presented the situation so far. Let's now play the game in a different way, and let's pretend that this different game is kind of equivalent to the original way, okay? We will fix a graph, perhaps a random graph, and we will endow each vertex with many more colors than necessary. So let's say the chromatic number of the graph is 5. So originally, you give each vertex 50 colors. Okay? So now we look at 1, 2, 50 to the end. There's going to be a ton of solutions in there. And precisely because you have so much freedom, the number of colors you have is so much greater than what you need, you can easily imagine that set being rather spherical. Where spherical corresponds to independence. Sphericity and independence go hand in hand. Okay? Meaning that, for example, if I tell you what color is this vertex, this gives you very little information as to what color will be a vertex fairly close to it. Okay? And now, rather than adding more constraint to the system, let me constrain the system by saying, okay, we started off with 50 colors. Let's now go down to 49 colors. Okay? So what does that mean? It means that you take the 50-dimensional object and you take a slice. Okay? And now that's your new set. Now I say let's go down to 48. You take another slice. So this result is as surprising as the fact that if you start with a high-dimensional object and you slice it, even if it originally was nice and convex, it will at some point shatter. Okay? So for example, if you take the surface of a three-dimensional sphere, that's pretty nice. It's pretty well connected. You slice it once, you get a rim. That's also connected, but not as nicely connected as before. And then you slice it one more, and you just get 2 points. Boom. Okay?
I think I get that.
Okay.
I mean, to me, this is like a proof that the universe has a lot of slack in it, basically. That the universe has to have a lot of slack.
Well, maybe, I don't know. Maybe we can talk about that, about the universe having slack later. So, now one thing which is particularly nice is that if you look at these computations that the physicists make, okay, they might be non-rigorous, but nevertheless, they do make explicit predictions about the location of this point. And if you look at their derivations for this number, their derivations have absolutely nothing to do with algorithms. Okay? There are no dynamics, for example. You just write down something, la 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 la, something has to be less than 1, 1 doesn't get to be less than 1, that's the point. Boom. Okay? And guess what? I mean, the number that they predict corresponds with the algorithmic barrier. Okay? With the point where we empirically know that algorithms stop working. So now we now have two very independent pieces of evidence. One is the fact that algorithms in practice stop working at this density, and the fact that we have these heuristic computations by physics that say, yeah, that makes sense, and that's the reason. Okay? So the contribution is to turn this into a theorem, to just prove, yes, that's what it's like. So in order to state the theorem in a way that is sort of, not physicsy, I'll need a few definitions, but the definitions are pretty natural and not that many. Okay? So I have systems with n variables, all of which have a common domain, let's say 0, 1. And I have what a physicist will call an energy function that takes a configuration of my system, a value assignment, and maps it into the integers by counting the number of violated constraints. So this is the energy function. A value assignment is a solution if and only if it has energy 0. It doesn't violate anything. Two solutions are adjacent if they're having distances 1, so they only differ in one value, in one variable. Now, under this notion of adjacency, let me say that a cluster of solutions is a connected component of solutions. Okay? So I interpret 0, 1 to the n as a graph, where the edges correspond to things that have having distance 1. I look at the subset of things that are solutions, and I say, okay, what are the connected components of this? And for technical reasons, it will be convenient to allow me to also define the notion of a region, where a region is a non-empty union of clusters, okay? But I promise you that I will not be abusing this definition in the sense that I will only actually tend to sort of merge together into a region clusters that are nearby. Okay? And finally, something which is very important is if I give you a sequence of states, a sequence of truth assignments, will this define a path? I will say that the height of that path is, so if I start at this configuration and I end up at this configuration, and let's say here I was violating 3 constraints, here I violate 7 constraints, I keep track of all the states through which I went, how many states was I violating, and I take the max. Okay? So it's literally, if you want to cross a mountain, how high do you have to go in order to cross the mountain? So these are the definitions. And now let me say that the set of solutions of a constraint satisfaction problem, so the set of solutions of an instance, I, is shattered if all of the following hold simultaneously. The first one is that there are exponentially many disjoint regions. And remember that a region contains one or more connected components. So therefore, there definitely are exponentially many connected components. Okay? None of the regions is particularly significant. So each region only contains an exponentially small fraction of all solutions. Okay? So if you think of this big green thing I drew before as a boulder, this boulder shatters, and the biggest piece in which it shatters is still a pebble. It's not the case that half of the boulder stays intact and then the rest shatters. Okay, no, the whole thing shatters. Every pair of regions has linear Hamming distance. So one region is here, then within a linear Hamming distance there is nothing, there is a void. Okay? And then finally, if this is a set of solutions, and this is a different set of solutions, a different cluster, you cannot transform these into these without violating a linear number of solutions in between. Okay? So if you look at the three-dimensional picture I was referring to before, I'm basically telling you that around each of those small green dots, it is completely landlocked by mountains. Okay, you cannot escape. Which means that the nature, if you wish, of the solutions is very different between different states of the system. Now, one immediate implication of the set of solutions being shattered is that if you attempted to sample solutions, even if I gave you a single solution for free, and you attempted to sample solutions by something like Markov chain Monte Carlo, you have absolutely no chance. Because your algorithm will at some point have to go against gravity for a linear height. Okay? It's like you're flipping a coin that's 1/2 plus epsilon, 1/2 minus epsilon, a linear number of times, and you expect to win in the 1/2 minus epsilon direction. Well, it's just not going to happen. Okay? So one of the areas in which this kind of approach has nice results that we're sort of currently writing up is if you look at games in which each of the players is a variable in the system, and these are so-called random polymatrix games. So you have, each player has a set of actions. You can think of this as the colors that are available to it. Okay? And it participates in a number of games corresponding to the edges. And the payoff is, well, I have to commit to one action, which will be what I will be playing in all the games simultaneously. And my payoff is the sum. Okay? So for example, in the graph coloring game, the payoff of a vertex is the number of edges in its neighborhood that it manages to break. By break, I mean to make bichromatic. Okay? So you could imagine that you have such a system, a random polymatrix game, and that you play best response, noisy best response dynamics. Okay, so you start at a particular configuration, and then each player has a clock. They wake up, they look at their neighborhood, they say, what's best response to this? Blah. Well, I will do blah with probability 90%, and something random with probability 10%. Okay? So you can imagine this as a natural model for how a market might eventually converge to a good solution. And the theorem is there exists some regime of connectivity in which this is a good algorithm. So the market will find a solution through the independent actions of lots and lots of agents. But then there is another big regime in which there is a tremendous price of anarchy. Okay? Meaning you need communism. You need someone to sit above and tell everybody what to do if you're going to be able to get in a really efficient state. Okay? So here are the theorems. So remember I told you that if I have k colors, there exist colorings for density up to this, k log k, and that the stupid algorithm works all the way up to 1/2 k log k. Well, then the theorem says that everything in between is shattered. So the reason we cannot make algorithmic progress is that up to this density, 1/2 k log k, is one nice big fat ball, but between this and this, we have this crazy world with exponentially many pieces. And similarly, for KCNF formulas, remember we had 2 to the k log 2. That was easy to establish as an upper bound. And then I said that recently someone showed an algorithm that works up to 2 to the k over k log k. And now the theorem is for anything in between those two, the world is shattered. Okay? So this theorem is basically say that if you want to be able to beat either this or this, we really need a new class of algorithms that operate very differently from anything that we have sort of seen so far. Okay? It doesn't say, obviously, that P is different from NP, but it puts forward a very, very concrete obstacle to algorithms. So if your algorithm is going to do well, it has to be able to manipulate this terrain. Okay? Because this terrain, in other words, terrains as ugly as those that I described are generatable in polynomial space. Okay? There exist small objects that generate terrains that are as nasty as this. So if you're going to have a polynomial time algorithm, it better be that it can navigate that, if nothing else. Okay. I could stop here. That might be a natural point to stop. Yeah? Okay. All right. Thank you.
Questions?
So I'm not an expert in computer science, and so I might be missing something very obvious. But it seems so. You showed a nice analogy between the phase transition, the energy landscape,
Yes.
and so on. A large hill between those shattered pieces,
Yes.
and so I can see how local search type of algorithm would
That's right.
fail because of the
That's
reasoning that you said. But isn't the stochastic random algorithms
It's not the only
supposed
game
to-
in town. That's right.
supposed to sort of have a more global?
No. But that's a great question. So consider, yeah, this is a very, very nice question.
Doesn't it depend on how you define the randomness?
Yes, but my point is any view of the randomness that is global, okay, is going to lead to an exponential time algorithm. But let me
like
say
the
something.
backtracking.
But let me say something which is sort of a very nice point that was made. Imagine that rather than having each constraint be a clause, which out of the 2 to the k constraints, for 2 to the k, variable value assignments, forbids 1. Imagine that it was an XOR constraint. So it forbids half of them. So it says, among these 5 variables, the number of variables that should be receiving 0 should be an even number. Okay, so this is a parity constraint. Now, if I write this down, this is simply a system of linear equations modulo 2. Okay? If you look at the energy landscape of this, it is exactly like satisfiability, like random SAT. We can prove this. Okay? So SAT versus parity have the same energy landscape. Yes? But SAT, we have no idea how to solve. Whereas parity, we know how to solve by Gaussian elimination. Okay, this is just a system of equations modulo 2. Yes? So I think at first sight, this might be an argument that says, okay, then basically your entire talk is bullshit, clearly. Right? Clearly what you say is worthless. Here's evidence that you can have an incredibly ugly energy landscape, yet the problem is easy. Okay? Now there's two counters to this. The first one is the problem that is easy to solve is whether this system of linear equations has a solution or not. Yes? But if you give me an over-constrained system of linear equations, and you ask me, find a value assignment that minimizes the number of violated equations, that problem is anti-complete. Okay? So the generic minimization of the energy function is anti-complete, even in the case of linear constraints. Okay? The only case in which it is polynomial time solvable is whether you're asking to whether it can be 0 or not. Okay? That's one. And now let's look at this question. When you ask, is it 0 or not 0? The lowest state energy, yes? If you look at Gaussian elimination, it does not proceed by maintaining some kind of state which it keeps improving. What is nice is that Gaussian elimination operates syntactically on the input. Yes, it's something that we teach kids in 3rd grade how to do, right? You say, take the lowest two equations, go all the way to the left, look at these two numbers, divide them, find the appropriate multiplier, multiply this one through, add up, and now here you get a 0. Yes? Then you move to these two, and then these two, and then these two, and then these two, and now the first column is diagonal, right? Then you proceed to the next column, and then you diagonalize the system. And now after half of the system is thrown away, this is zeros, you just start plugging in. Yes? What's the important point? The important point is that we have algebraized the problem. Meaning we have developed an algebra which syntactically operates on the input and makes progress. So for satisfiability, the analog of that would be something like, let's say you have one clause that contains variable x1 positively, and another clause that has x1 negatively. Okay? It is true that by resolution, these two imply the clause in which x1 is gone. Because x1 is going to be either true or false. Okay, therefore, you will be satisfying this joint clause. Okay? The problem with this algebra is the following. If the original clauses both had length 2, yes, then the new clause, the resolvent, will have size 2, which is good. But if the original clauses had size 3, and you bring them together, the resolvent will have size 4. Okay? So the algebra doesn't have closure in itself within polynomial representation. Okay? So in principle, okay, in principle, you could prove that P equals to NP by two ways. One is by developing an appropriate algebra for satisfiability. Okay, one that operates syntactically on the input, completely ignores this landscape business. By some miracle, I don't know. Okay? It could be possible. I'm not saying it's not possible, okay? That's one way to try to do it. But all proof systems that we have, remember that to solve satisfiability in linear time, it basically means that you can prove that the formula is unsatisfiable with a polynomially short certificate. Okay? So good luck. Okay? Or you could try to prove that P equals NP because you have some incredibly clever way of navigating the energy landscape. And then what the message of this talk is, look, one of the landscapes that you will have to navigate is this. So keep that in mind. Does that make sense?
That's very helpful. Thank you.
Sure. Any other questions?
More questions? Sure. This also kind of got left field, but I was imagining the description of this simplex, this hypercube, and flattening it into a random graph, and then initially you have something that would be almost fully connected, and then as you start want to say.
Adding constraints.
Yeah, adding constraints. You
That's
start randomly removing
Disconnecting
a random
parts.
subset
That's right.
of links, and then at
That's
some
right.
point you get a transition from a connected graph, giant component, to a bunch of scattered
That's right.
graphs.
That's right.
And so I'm wondering, I mean, that transition has been studied, right, a lot in graph theory, like in terms of when, with like, if you have randomly distributed degrees, and I'm wondering if there's a mapping of some
The problem here is that the object that you're playing with has exponential size now, not polynomial size. So capturing all the internal paths connectivities of something like this is very difficult. So for example, if you look at, so one problem you can think of is, I have n vertices, I take the clique, everybody's collected, and then I remove every edge with probability p. Okay, that's just standard percolation, the world's best studied problem in probability, yes? Now take the exact same problem, but rather than playing it on a clique, play it on the hypercube. So you take 0,1 to the n, and remove all of these edges having distance 1 with probability p. So it's percolation on the hypercube. This is exponentially more difficult.
Okay.
Okay? It is a much, much harder problem to do percolation on the hypercube. Because you don't have, you see, the clique doesn't have a geometry. The hypercube has some geometry. Okay? So as soon as you have geometry, things become much, much harder.
All right, let's take this